Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to continue our discussion of bolted connection design by talking about the yielding failure modes. So yielding in bolted connections is a very similar approach to the approach we took to yielding in nailed connections. We're still using the Johansen yield equations, so the detailed explanation of those equations can be found in the nailed connection videos. I'm going to only gloss over the equations themselves. There are some minor differences, though. Okay, so the embedment strength, well, similar. The equations are very similar. In fact, one of them is identical. For nails, when we had nail embedment in a piece of wood, it didn't matter whether we were going parallel to grain or perpendicular to grain. We had the same strength. We had the same embedment strength, like the nail pulling through the piece of wood. For bolts, since they're bigger, there actually is a noticeable difference between loading in this direction and loading in this direction. So the strengths are different in those two directions. And so for loading on an angle to grain, like on a diagonal, there is an interaction equation built into the embedment strength equation for nails, which we will see. Okay, the second one is that the KD, KSF, KT factors are in a slightly different place. Before we had them kind of outside the embedment strength. Now we have them right in the embedment strength. So when I calculate F1, F2, the KD, KSF, KT factors for the wood material, parts of the embedment equation are embedded there directly. And that is to separate it out from consideration of so we're not applying those KD, KSF, KT factors to steel parts of the connection, basically. So in nailed connections, we had this embedment strength F3, which was for times when we were having yielding combined with embedment failure. So when we had a nail and the nail was bending and yielding significantly, and we had this geometric effect where as the nail is bending, it is also being engaged in tension as it has a significant deformation, and that increases the strength, and we called that the rope string effect, the rope effect, some places call it the string effect, but we don't have that effect in bolts. It's basically because the aspect ratio of a bolt is thicker. So when I have failure of a bolt, I'm not going to have huge deformations like I do in nails, at least not as large as in nails. For a thinner bolt or a bolt that's very long, I might get that effect, but in the general case, I won't. So they just leave it completely out of the equations. And that, of course, is a conservative approach. So even if I had a really long, slender bolt, and I did get some of this kind of string effect happening, this kind of tensioning effect, for most cases, it wouldn't be present. So it's left out of the design equations entirely. Okay, so the other difference is that the thickness calculations are different for bolted connections. First of all, there's no minimum thickness requirements like there are in nails. Like there's no requirement for a certain penetration depth for a nail into a piece of wood. And that's because the bolt goes all the way the pieces of wood and then is connected on the outside. So there's no worry about it pulling out prematurely because it has a nut and a washer. But it's the same for dowels, actually. Even those that don't have nuts don't have those requirements. And also the calculation of the thickness is quite straightforward. For example, okay, so here are two examples of some different bolted connections. One that's a wood-wood. One is that the one on the right is a steel-wood-steel. Clearly, so in these cases, and this is not all the possible cases that you would run into, I'd encourage you to go to the standard. They have some more examples of how you would calculate these thickness requirements. But basically, usually the thickness requirement is not the thickness requirement, but the thickness that you use for the calculation is just the thickness of the piece of wood that's being connected, because the bolt goes all the way through from one side to the other. The main exception to that is if I have a countersunk hole like this, where I have routed out a little space so that the nut can fit within, so that the nut doesn't poke out from the surface of the piece of wood. You know, like that would be an aesthetic thing. So if I had a piece of wood like this and I had my bolt, you know, I may or may not want to be able to, I may or may not want my bolt to actually be poking out proud of the side of the piece. It's really hard to show here. So I can have it poking out from the side, or if I like, I can write out a little hole so that the top of the bolt or the nut is flush with the surface of the piece of wood, so that basically the whole surface of the piece of wood doesn't have anything poking out. So that's an aesthetic consideration. But if I do that, basically all of the wood that is the thickness of that bolt basically becomes useless for the connection. So basically this material here for the whole length is not considered at all. So this material basically is considered not to exist. Okay, so that makes sense. And then, you know, if I have a steel wood steel connection like this, then this main member, which is member 2, T2, is just the thickness of that piece of wood. So easy peasy. Okay, so how do I actually calculate the resistance of a piece of wood now using the Johansen yield equations? Okay, so just like in nails, I calculate my resistance for each bolt, like for a single bolt, so that's why it's a unit lateral yielding resistance. And I use the Johansen yield equations to do that, which has the 7 modes, which are the same as before, except with a just slight difference that we do not have the F3, like we already discussed. Okay, so these are effectively the same Johansen yield equations as before. I've identified the places in red where we have replaced F2 now with F3. So we're just using the regular embedment strength F2 instead of the embedment strength where a nail is yielding. So we don't have that rope string effect anymore. So these are 7 modes, just like before in nails. Some of them apply to 2-member connections, some apply to 3-member connections, some of them apply to both. So we don't check all 7 for every connection. Depends on if you have a 2-member connection or a 3-member connection in the same way as for nails. And of course, in the standard, it has all the drawings that go along with these, but I don't think it's necessary to put those here because we've already talked about them in detail. So those are the unit lateral yielding resistance equations for NU from the Johansen yield model. Okay, so now we need to be able to calculate our embedment strength for all the different types of members that we can have. So first for wood members. Okay, so we have F1 or F2, so depending on whether we're talking about the side member or the main member, like the member in the middle or the member on the side. If I have 2 members if I have a 2-member connection, then one of them is F1, the other one is F2. It doesn't really matter which one is which then. I'm going to represent that by this factor Fi theta, which is the embedment strength at an angle to grain theta. So if it's parallel to grain, it's going to just be the P, FIP. If it's perpendicular to grain, it's just going to be the FIQ. And we're going to see how that works in a second. So Fi theta is, you know, the I is either F1 or F2. And the theta means at an angle to grain. So Fi theta is basically an interaction equation that looks like this. And there's the KD, KSF, KT as well that's brought into the embedment strength equation like we talked about before. So this interaction equation takes into account the interaction between parallel to grain strength of embedment and perpendicular to grain strength of embedment. So P is the parallel to grain one, Q is the perpendicular to grain one. You can imagine that, for example, if, let's say theta, okay, so theta is like this. So here's my piece of wood. Okay, so if that's my piece of wood and that's the angle of the load, then theta is the angle between the grain direction and the load. So if that's my grain direction, then theta looks like that. Okay, so you can imagine that, like, let's say if theta was equal to 90 degrees, so then it's directly perpendicular, right? Then what's sine 90, right? Sine of 90 equals 1, right? Cos of 90 equals 0. So sine squared of 90 is also 1. Cos squared of 90 is still equal to 0. So then that would mean that my, let's keep it in orange. Let's say then my Fi theta is going to be FIP, FIQ. My sine theta is going to stay. So this is going to be FIP times 1 squared. And then FIQ is going to be times 0. So it goes away. So then I cross out my FIPs here and I get that Fi theta equals just FIQ. So you can see just the way that this equation works. If I'm directly perpendicular to grain, so my theta is 90, then my Fi theta is just equal to my FIQ, which is my embedment strength perpendicular to grain. So if I have my load directly parallel to grain or directly perpendicular to grain, I don't really have to do this interaction equation. I don't have to calculate the perpendicular to grain strength, for example, if I'm doing parallel to grain, because we know it's going to cross out. So if I'm doing embedment parallel to grain, then I just set my Fi theta to FIP. And if I'm doing embedment strength and all my load is perpendicular to grain, then I can just set my Fi theta to FIQ, which is the embedment strength perpendicular to grain. So then what are those embedment strengths? So for the parallel to grain embedment strength, so theta equals 0 degrees, basically I have 50G times 1 minus 0.01 dF. So it's dependent on the diameter of the fastener again, and you will notice that this is the exact same embedment strength equation that we used for nailed connections, and all nailed connections had this embedment strength. What's different is the addition of the perpendicular to grain strength. Then our embedment strength perpendicular is a lower strength. And so it's the same kind of equation as FIP, but just with a 22 coefficient instead of a 50 coefficient. So it's just weaker in the perpendicular to grain direction, as you can imagine, because in the perpendicular to grain direction, when my bolt is going into the grains like this, it is crushing the grains perpendicular to grain, which is a weak way to crush the fibers, right? The fibers are weaker in this direction than they are in the longitudinal direction. So it all makes sense. Okay, now what about for other types of members? So we need to have an embedment strength for steel. This is not the design of the steel plate, of course. This is just the embedment strength for the calculation of the yielding modes of the bolt combined with crushing of the wood. For the strength of the steel plate, you need to calculate that separately using S16, which is the steel design standard. Okay, so this one is similar to what we had for nails. You might recall an equation that looked something like this, where F1 or F2 is KSP phi y times FU. And this is different in the sense that this used to be phi wood, and now it's phi y, which is the yield strength of the nail, the bolt. Okay, so where we have different combinations of factors KSP and phi steel, whether we're dealing with mild steel, which is like structural steel plates, or if we're dealing with cold form light gauge steel, like all of the brackets and holding brackets that we use at the end of wood, like joist hangers and stuff like that, are made of cold formed light gauge steel. And then we have our phi y and FU. I think I misspoke before. FU is the specified minimum steel tensile strength, not the bolt strength. I might have said it was bolt strength before. It's not FY, it's FU. And they give some suggested values for that in the standard, but it's basically the steel tensile strength, the ultimate tensile strength of the steel plate that we're using for our embedment calculation. Then if I have concrete or masonry, so let's say if I had a bolt embedded in, like I had a anchor bolt embedded in concrete or masonry, like a foundation or something like that, and then I had my piece of wood on top, and that piece of wood was bolted, then I just use the F1 or F2 value of 125 MPa for the embedment strength of masonry. So this is not compression strength, this is embedment strength. So this would happen, you know, bottom plates in a light frame shear wall that are bolted down directly would have this kind of embedment strength for the concrete side. Or if I was bolting something into a masonry wall or something like that, it would look like this. And then of course I have the dowel or bolt strength for the bolt itself. So for the bolt itself, if you use an ASTM A307 bolt, which is a common bolt grade for timber connections, you can just use 310 MPa for the FY. If you use any other bolt, like if you use a A325 bolt, which is a common bolt for structural steel connections, which you could definitely conceivably see in a wood connection, having in a wood connection, then you basically take the average of the bolt yield and the bolt ultimate strength, and you set that equal to the yield force. These must be based on test data, certainly. Okay, so now that I have all of my embedment strengths, my F1 and my F2 and my FY, and my FI theta for the wood parts of the connection. So depending on whether I have wood, then I'm only going to be using this FI theta. If I have steel wood, I'm going to use the steel embedment strength for the steel side of the steel side, and the wood one for the wood side. And then I'm going to plug all of those values, including the bolt diameter and the thicknesses of each side of the connection, and calculate my lower bound NU, right? I'm going to use the lowest of all of these, obviously, just as we did for nailed connections. So I find all the 7 mode strengths, and then whichever one is minimum, that's the one that's going to govern, and that's what I'm going to use to calculate my total lateral yielding resistance, which has an equation that looks like this. Okay, so an important thing is that unlike the row shear and group tear out failure modes that we're going to talk about in a minute, the yielding resistance is for the entire connection. So later in a few minutes, we're going to talk about how, you know, usually if I have a 2-member connection like this, I'm going to calculate row shear for this side of the connection, and then I'm going to calculate row shear for this side of the connection, because they could have different geometries, these 2 members. But for yielding resistance, I only have one check, and it's for the entire connection together. So I don't check like this side and this side separately. I just check the entire connection. I have one yielding resistance, because those Johansen yield equations include all of the members that are connected together. And by necessity, it has to do that, because we have to calculate how the nail is bending through all of those connections and how the embedments are affected. So this is only one lateral yielding resistance check for the entire connection altogether. And what we get is an NR, which is our total resistance to load. Okay, at any angle to grain, it doesn't matter. We've already taken into account angle to grain when we calculated our wood embedment strength, F1 or F2, which was based on FI theta. And so we get our reduction factor times our individual per nail strength times our number of shear planes, just the same way that we did for nails, times the number of fasteners. So it's very straightforward, this final equation. We don't have our KD, KSF, KT in this equation because we already took care of it inside the wood embedment strength, which is different than what we did for nailed connections. Okay, number of shear planes and number of fasteners. So with that, that's the entire approach to calculating lateral yielding resistance. So that's the first type of failure resistance that we have to check for bolted connections I'm going to put a cut here, and in the next video, we're going to talk about, we're going to start talking about the brittle failure modes, which are row shear, group tear out, and net tension.